So good afternoon to everyone attending today's webinar on financial engineering using the Maple approach. Welcome and thank you for taking the time to join. I hope to give you a high-level overview of our functionality with respect to finance, as well as give a roadmap for the future. So the theme of today's webinar is financial engineering using Maple. This is, of course, a complex and multidisciplinary field involving finance and economics, mathematics, statistics, engineering, and computational methods. The aim today is to give you a high-level overview of Maple's approach to solve problems in this domain and some of the innovative features of the technology that can save you time in your processes. So some of you will already have some experience with Maple and others may not. For those of you who haven't seen Maple before, I'd like to spend the first part in orienting you into what Maple is. That will hopefully help you better understand what Maple is and place the rest of this presentation and demonstration into context. And after that, I'll discuss our value proposition for financial modeling and analysis in a little greater depth. So firstly, I'll just give a little bit of history as to what Maple is. So Maple began its life as a tool that was developed to perform mathematical computation or computational algebra, also known as symbolic computing. And this was at the University of Waterloo some 25 years ago. And we celebrated actually our 25th anniversary last year. You can see a timeline of Maple's development on our website. These are some of our customers and partners. So Maple is a tool which combines symbolic and numeric computing into one workflow through the Maple document environment. It enables you to quickly derive, explore, and visualize your concepts and data, and also prototype scenarios through its function library and its programming language. So underlying this intuitive approach to problem solving is a highly developed programming language for developing algorithms and building the analysis instruments required to better understand your data. Knowledge is captured in a natural form, which has been our philosophy for a long time, within the document-oriented workflow. And this seamlessly integrates with common processes and components for design and analysis, such as calculations, text, diagrams, and external applications. So let me jump into Maple now to show you some examples. So when you first load Maple, you will see our starting workspace. Here you can get a quick access to useful resources. For example, within the finance section, so here we have several example worksheets to show you how Maple can be used in this particular domain. If we open an example, here we can see how a Maple worksheet is structured into sections. And text is combined with mathematical calculations. We can also see calls to various Maple library functions, which I'll go into a little bit more detail through the presentation. So just to show you how Maple works, when you start an empty Maple document, you're presented with this whiteboard-style interface. Our aim is to allow our customers to work in an environment that feels as natural as possible. Now, this includes using standard mathematical notation everywhere, but also including text. So I can very easily use this worksheet as a word processor. So this is ordinary text. This document describes the analysis of, for example, and we can have sections. so I can put this into a section. And multiple sections can comprise my worksheet. And mathematical regions are also incorporated into the same environment in a seamless way. So if I wanted to insert a mathematical expression here, I can very easily insert it, and I can also calculate. So this also gives me access to the Maple function library in a seamless way. Now, when I execute this region here, Maple has gone off and calculated this result. And I can very quickly visualize this result by simply right-clicking on the object and getting a context-sensitive menu and getting a plot of this result. And if something changes in my document, so if I change this equation, for example, I can re-execute the worksheet and the result propagates through the rest of the worksheet. So it's designed to be easy to use, so users can create the same sort of documents that they would see in textbooks or on their whiteboards or in their notebooks. So if I close that document down for a moment, here is a document that has been prepared earlier. Maple documents are highly customizable. In this document, we have several sections which organize the worksheet. If we export this worksheet to an ebook, for example, we can also set up Maple to automatically do the typesetting and the document features similar to a LaTeX type of approach. In fact, Maple documents are also LaTeX compatible. Now, this is not exhaustive, but should give you an understanding of the philosophy of Maple, these examples. So many people use Maple to algebraically manipulate formula and equations. So this can eliminate the error that would naturally creep into the manipulation of equations by hand. So in this particular example, let's say I have an interest rate R, that's lowercase r, which compounds at a discrete frequency f1 over a time t with a total return g1. Let's say I want to express this interest rate R in terms of another compounding frequency, F2, with a total return G2. So with an interest rate being the lowercase r and a compounding frequency F1, G1 would be the total return expressed in terms of another compounding frequency. The total returns G1 and G2 in both instances would be the same. So I can use Maple solve command to solve this equality for R. So I can type in the solve command here. With the relationship that I am wanting to solve. And the variable that I want to solve for, which in this case is R. So this would be the new interest rate expressed in terms of the new compounding frequency F2 and the old compounding frequency F1 and the old interest rate. So the solve command is a Maple library command. And Maple has several thousand functions covering virtually every area of mathematics. But you don't have to know these commands to become immediately productive with Maple. We have support for context-sensitive menus. The context menus are far more flexible than this. Let me give you the example. So G So if I right-click on the expression at hand, I get this menu pop up, and I can once again go to the solve submenu and solve for variable r. And I can get the result here. Note that all of the equations are in natural math notation with subscripts for powers, overline division. It's very readable, and if I did make a mistake, it would be very easy to spot. We also have support for numerical operations, and this is just a simple example of the fsolve command. We can also do far more complex operations as well. So here we have plotted a binomial tree. You could use this to price an option using some kind of backwards induction. Also create stochastic processes and visualize them using Maple's plotting tools. We can also create interactive applications like this. So instead of exposing all of the maths and the logic, we can actually create an interface that hides all of the complexity. Here I have input boxes which allow me to change parameter values. So if I change one of these values here, I can ask Maple to regenerate this sample, for example. I can now deploy these applications to the web using one of our other tools called MapleNet. Now, MapleNet, using MapleNet, anybody with a web browser would be able to interact with this application. They'd be able to change parameter values and get updated results. And there are many interactive elements to choose from when creating your worksheets. Now, many financial engineers use Maple to develop new financial instruments. And without going into too much detail, I would like to give you a sense of what we can do at the higher levels of financial engineering. So, for example, the standard Black-Scholes model assumes the returns are log-normally distributed. However, in reality, returns distributions have skew and kurtosis, which are fat tails, and often include the possibility of low-frequency, high-impact events. So here we are modifying the standard Black-Scholes model to include jump diffusion, which introduces concepts like skew and kurtosis into the returns distribution to make it better reflect reality. Maple also has extensive connectivity options. It can connect to many other packages. It can also connect to the web and web services. This is an example of an interactive stock quote importer. So this is importing data of stocks from a start to an end date. The data is then taken into the Maple environment, and you can do further analysis work on this data through the Maple function library. So, for example, here we are reading in the data and we are just visualizing the data. And since the data is now available inside of the Maple document, I can now use these stock prices to optimize a portfolio, for example. So let's now take a step back. These example applications point to the general philosophy of Maple. So you write down your equations or import your data. You can then solve your equations or analyze your data using the function library. and your own algorithms, and then view the results in different forms. So why Maple? Well, Maple is a document interface. It allows you to capture your knowledge quickly and efficiently. It's very readable. You don't need to be a Maple expert to read Maple documents. There's a strong mathematical functionality built into it, so this enables you to do faster problem solving and also integrate with other financial tools in your workflow. There's also quite a strong programming language, which I'll talk a little bit more about in a minute. There's also connectivity to external data sources. You can also deploy your Maple applications once they are developed inside of Maple via a web-based server, or you can code generate to external languages. And the Open API actually enables you to connect the Maple kernel to your own custom applications. And we have spent a lot of time in developing our parallel processing capability. So our programming language is conducive to parallel processing. And programming is a key strength for our customers. So it's a procedural-based type of approach. So it's easy to program algorithms if you're familiar with the traditional procedural type of programming languages, such as C or Python or MATLAB, for example, but also incorporating other elements, object-oriented and functional elements as well. Now, Maple itself has a design heritage of 25, 30 years. So in that time, we have developed partnerships with customers, and these are some of the application areas. So people are using Maple to prototype new financial instruments. They use Maple for backtesting data, portfolio optimization, calculating financial ratios, and connecting to financial data providers as well. So let's take a look at a couple of applications so you can see what we do. So you can price options using a variety of payoffs, including custom payoffs. Let's say, for the sake of argument, we have a European strangle, which pays off if the underlying asset deviates more than 20 units from 100 in either direction. It's a relatively simple problem, so we can create a function right in Maple now. So our payoff function, S, will be defined as the maximum of S minus 120 and 80 minus S. So the maximum of those values. Once I have my function defined, I can visualize my function using Maple's plot command. Let's say between 70 and 130. Now we have defined our payoff function, we can now price a European option, for example, using the lattice method. Now we are using some of our built-in financial functionality. So this is showing a binomial tree using the Black-Scholes method and priced it using a lattice method. We have support for optimization. Here is an example of our optimization functionality. Financial analysts often use a quantity called the Sharpe ratio. to quantify how effectively a portfolio of investments uses risk to get return. A higher Sharpe ratio is usually better. Now, if you have a portfolio of assets with these returns over 12 time period, you can use Maple to calculate the Sharpe ratio. You can then use Maple's optimization algorithms to maximize the Sharpe ratio. Financial analysts also use a series of financial ratios to gauge investment worthiness. So here are some examples. Let's take a look at one of these. For example, the omega ratio. The omega ratio divides the returns distribution into two halves to incorporate non-symmetry into the distribution. So in this example, we have 10 returns. This could be any number coming from external data with a minimal acceptable return of 1%. We can then use Maple's functionality to select those returns below and above the minimal acceptable return. If you divide one by the other, you have the omega ratio. So moving on, we've already seen how Maple can connect to web-based data providers via the web. Here's one more example. This is a simple Maple worksheet that connects to a web-based provider of Forex data. It plots the exchange rate for two currency pairs. And this is actually using some of Maple's programming language to get the exact result that we would like. So if I just minimize my palette here, you can perhaps see the plot a little better. So if I change this, for example, from USD to GBP, and perhaps change the dates, you can see how Maple has gone off and brought in the data. So the middle line represents a moving average, and the two lines either side represent the Bollinger Bands for these set of data. So these are some of the application areas our users have exploited over the past. So the financial modeling functionality that's built in enables you to manipulate term structures of interest rates. There are lattice methods, calendar and day counting tools, different kinds of financial instruments and bonds and swaps and swaptions available. As a broad overview of what's available, there are individual functions for data arithmetic and cash flow analysis. We also have support for interest rate structures and lattice methods as well. There are tools for short rate methods and stochastic processes, as well. I'm not going to go into a great deal of detail on all of these functions, but I'm going to show you an example here of one of the functions, which is a geometric Brownian motion, which is a process functionality. So if you look at this example we have, this is now doing a path plot of a stochastic process, geometric Brownian motion, with an initial value of 1, a drift of 0.2, and a volatility of 0.06. And if I change the path plot, I can equally visualize a single replication or 10 replications. So an Ito process is slightly more general. Its value can be a value of a function of state and time. So we can define that as a function inside of Maple. So if I define this function, let's call it IP. And the function name is called an Ito process. And we can include an if condition here. And we can state that if the time is less than 2, let the volatility be one value. And obviously, if it's greater than or equal to this value, then let it be something else, slightly higher. So our volatility will increase at time is 2. So now we have our Ito process defined. We can visualize that, again, using the path plot command. And you can quite clearly see that after 2 seconds, time variable 2, the volatility increases. So also we have a suite of strong optimizers for performing tasks such as mean variance portfolio optimization, sharp optimal portfolios, maximum likelihood estimation, and local and global optimizers. There's also tools internally for Monte-Carlo simulation. There are built-in probability distributions, and you can also define your own probability distributions. There's ability to compile your code from within Maple, and this can significantly increase the execution speed of your code. So once again, the connectivity is an important feature for us. So we endeavor to be able to connect to other tools in the tool chain. So as well as the HTTP and FTP connectivity, there's database connectivity, Excel connectivity, and through the Open API, we can connect to other tools in your, other applications in your workflow. Parallel processing is, again, an area where our programming language can be used to increase the speed or distribute the computation over multiple cores and grid networks. So there's a new technology that we've been incorporating into our product suite called MapleSim, which enables us to represent a process model in a visual environment. Let's say it enables you to create a system-level model for the different processes that are there in your network. So a process model is an aggregation of one or more models based on equations. And so we will be showing some more details about applications within the system-level modeling approach for finance as well going forward. But to give you an idea about what I mean by that is, in terms of a visual representation, we can have a block diagram representation with certain inputs. Now, these inputs can be coming from different data sources, for example, and a block which computes a certain quantity. Now, in this case, we have a PDF function that's defined inside of this block. If I open this particular block structure, I am inside of a Maple document, and this block has calculated a certain probability density function based on our statistics functionality. And in a similar way to this, we can have multiple blocks interacting together in a visual representation, and then use this visual representation as a sort of a design for your processes, and then generate code directly from this environment to either run on high-performance computing or plug into your existing applications. So that's the high-level overview of some of our functionality in finance. Thank you for your time today, and hope to continue this series of webinars with more detailed sessions on each of the topics that we've covered so far. So thank you. Have a good day.